what I wanted to talk about today is a pretty high-level view of computing research. For the last 5 years, I worked at the National Science Foundation in the United States, and I led the Directorate of Computer and Information Science and Engineering. The National Science Foundation funds 87% of all of the basic research in academia and universities in the United States, and so part of my job, or our job there, was really to worry about these issues of where computer science research funding was heading and help sort of grow that pie and make sure that continued academic research in the United States sort of continues to feed economic competitiveness and national security, national defense, all those good things. So I wanted to take sort of a high-level view and give you some thoughts about where computer science research is heading. I've also been a professor for 35 years, and I think a lot about these issues about where universities are heading and where computer science departments in universities are heading really around the world, and I want to spend some time on that too. So I'll talk about research directions and some thoughts about where university directions are heading, also specifically computer science. This is my first visit to Korea, so first of all, I'm really happy to be here. I see everybody using your apps whenever, you know, I'm on the subway and looking around, so it's really great to be here. So I don't need to tell anybody here about how important computer science has been. It's really made foundational changes to how we live as people, no matter what country that you live in. And in the United States in particular, when we think about computer science research, and we have to tell the taxpayers of the United States, why is it that the federal government is investing in basic research? Part of that message, as you see here, is about economic development, economic prosperity, competitiveness, and long-term sustainable economy. So computing has really done some incredibly amazing things. Let me give you some statistics just about what's happening in the United States with respect to the academic community here. So let me start here in the middle. So these are the number of undergraduate students who are studying computer science. And you see this sort of almost, well, not quite exponential because there are only so many students, but you can't go up forever, but an incredible increase in the number of students who are studying computer science. In some of our universities, Princeton, for example, it's the most popular major on campus now, right? And so we have lots and lots of students who are studying computer science. Part of this is where the jobs are. If you look at where are the job openings in the United States between the new job openings between 2016 and 2026, the US Bureau of Labor Statistics says that across all of science, technology, engineering, and math, that 56% of the new jobs are in the computing field. Another 20 in engineering, and then you see the rest in the life sciences, the physical sciences, and in mathematics. So certainly, my observation is that this is driving a lot of student interest in what's happening in universities. And I'll mention just this graphic pretty briefly. The message is really down here at the bottom. What it's saying is that in the United States, when you look at universities, that over a 3-year time period, we've basically had a doubling of the number of faculty ads, so advertisements for new faculty. And so in the United States, where university sizes are pretty flat, maybe going down, doubling the number of tenure-track professors in computer science is really a pretty amazing thing. So we see lots and lots of growth. So I'm from the University of Massachusetts. Sorry, I should have mentioned that first. My department of computer science recently became a college of computer science. So we have a college of engineering, we have a college of computer science. And one of my jobs when I was there was to help convince the president of my university that this would be a good thing. So I went in and I met with my president and I said, oh, look at the growth here, look at the jobs here, look at all these good things that are happening. You as a university have to give us more money, hire more people, hire more graduate students. And my president said to me, I'll never forget this. He says, you know, Jim, everybody who sits in the chair you're sitting in says what they're doing is the most important thing in the world. And I said, well, you know, I can understand that, but in my case, it's actually true. So I just wanted to show you a picture about how I think about computer science, right? I don't know if you've ever seen this. There was a great poster, probably none of you were born. There was a great poster in the 1970s saying, you are here, right? It's sort of the picture of the Earth, you know, where the Earth is in the universe. And so this is the way I look at the universe, right? That computing is absolutely at the center of the universe. And when I said that to my president at my university, you know, and I think you'll see this as we talk more about sort of what's happening in computing and where it's going and its role in universities, that's a good view of the universe, okay? All right, so I want to say a few words about research directions at a high level, and I want to talk about, thank you.
Numbers and students, right? So you showed the numbers in 2017.
Yes.
So do you think it's going to grow?
It's actually the numbers for 2018, but there's a lag in reporting. That line is going up again in 2018. It can't go up to, and I'm not sure.
100K. 100K.
Well, you have to understand that these are research universities that are reporting numbers here. There just aren't that many students. It will have to flatten out at some point. I will tell you, so that's a great question. The question is, where will the growth come? Because these are traditional computer science majors, right? So they're people like I imagine all of you are, right? That you're into large-scale systems, you're into operating systems, you're into artificial intelligence, but you're doing a lot of coding, right? In my mind, there's only so many students who really love to do that, right? I mean, you'll never take, well, never say never. I think it takes a certain mindset to just know that you sort of love to do that, and there are some people who hate to do that, and that's fine. You know, if the whole world were made up of computer scientists, it'd be really not a world I wanted to live in, right? But I think where the real growth is going to be, and I'll talk about this later, is something that's called CS plus X, right? And that is you're majoring in humanities, you're majoring in social science, you're majoring in anthropology, you're majoring in English, communications, and you could take that major and combine it with computing, and maybe not the computer science major that you did, but to take maybe half of the computing courses and do what's called the CS plus X major. And I think that growth is going to be really, really big, right? And that's not charted here. These are just sort of the deeply technical majors. Great, so I'll come back to that. Okay, so when I joined NSF, well, so you all have bosses here, right? And so, you know, often your boss says you have to do something, right? So you just have to do it, and you have to do it the way your boss says to do it. So my boss said to me in my first year at the National Science Foundation that I needed to give a talk to her and to the other executives. And in one slide, I had to tell her where computer science had been, where it is now, and where it's going as a field. And I could only do it in one slide. So I did it. I'm going to show you a slightly updated version of that because things have changed. And of course, it's got lots of overlays and expansions and things like that. But here's my one slide overview of where computing is going. And then I want to dive down into AI in particular because I know it's of interest to people here. Okay. So you should think about it. How would you tell, you know, your parents or your friend where your field is going in one slide? So here's my best try at that. Okay. So if you majored in computer science, oh, wow, now I can really move. Great. If you majored in computer science, you might say, well, this is what my field is all about, right? And those are the courses and the books and the textbooks and things like that that you've read, and that's 100% fine, right? So to me, that's sort of the core, right, of what our field is about. But what I want to do is I want to talk about where these core disciplines are going. And I want to identify 4 trends for you, right? Because remember, where are we today? Where were we? Where are we today? Where are we going, right? So first, think about the technology building blocks. Now, most of you are probably computer science, not double E, but you know about CMOS and you know about circuits and systems. And really, that's the physical foundation about how we compute, or how we have been computing. But certainly, you can't, I'm sure you've all been reading about, Google and quantum supremacy and algorithms that are going to be able to, at some point, possibly in the future, crack public key cryptography, and we have to worry about post-quantum cryptography, things like that. So quantum computing, molecular computing. I don't know if you followed the work on DNA storage, but the notion that you craft DNA, you create strands of DNA, you encode the 1s and 0s in DNA, which is incredibly robust, has a long shelf life. You can basically stick it in a box in your house and read it out, N years later, and it's still in very good shape. So this notion that we're moving beyond electrical to these other forms of maybe bio-based or quantum-based computing is something that's happening. Okay, probably if you ask any of your friends, what is a computer? It's, it's the laptops that you have, it's the phones that you have, it's the pizza boxes that are sitting inside our data centers today, right? I'm absolutely convinced that my grandchildren, for instance, will be thinking beyond the box, that computing, and of course we see this already with IoT and the mobile edge cloud types of infrastructure, is that computing will be embedded all around us and at scale, right? So the kinds of things that your company is doing and a lot of other companies thinking about processing sort of back in the cloud, but interfacing with the user in the environment, always in the environment, is I think, again, this one's the easiest to predict because I think this is happening now. Okay? Okay. Third direction, what you might call HCI. For a long time, well, in the beginning, that meant sort of, a mouse and a screen and things like that. Then it became haptics, right? But now when you start thinking about, well, what does it mean to interface with a computer, I think especially at this company, it really means, I love this phrase, the human technology frontier, right? Because now what we're facing, so think about the ways in which we're interfacing with computers. It's not just the physicalness of how I control them, but what they do for me, and what they do for other people. So assistive technologies, what's called affective computing. Computing that understands emotion and adapts its interaction with humans on the basis of perceived emotion. Social informatics, this mind-machine interface, for people who are not sighted, being able to put silicon in neural pathways and optical pathways in order to be able to see and perceive, and brain science. And this is where a lot of AI sits, and that I'm going to talk about. And to me, this is obviously the huge growth field or growth area within our field. Okay, and then lastly, we've had a lot of applications. I put stovepipe there. Certainly, computing is touching so many different fields of science and engineering. I mentioned humanities, health, security, the environment, just anything that you can think of. Okay, so what do you think? One slide? My boss thought it was okay. She's an astrophysicist, so I'm not sure how much she really understood. Oops, we're being recorded. She won't watch this, but that's okay. Anyway, I just wanted to sort of leave you with that perspective, and then we're going to jump in here. One of the points I want to make, though, is that what we see happening here actually is going to have impacts here, here, and here as well. Okay? All right, so actually, let me stop there. Any comments Anything I left out?
Where's the AI?
AI, this is all AI here to me.
So small. No.
Is it too small? You know, I didn't scale it with respect to anything, right? You know, I think when you think about impacts on people, sure, that's way bigger. In my department, every year we have a retreat where we go away, usually to a nice place, and talk about the future. And this is where, you know, so much of our conversation is. Right? So you want it bigger? Okay. Somehow I'm not surprised. Any other comments? All right, so, you know, I wanted to, one thing that I think, because of all the excitement around AI, I know a lot of your folks are at NIPS and you can barely get into NIPS, you can't even attend anymore, right? And I want to draw a distinction, which I don't know how sort of clear this always is in people's mind, between what I want to call narrow AI, and that's not a negative, right? It just means that it's focused on solving individualized tasks that are performed just extremely well. So speech recognition, image recognition, translation, I mean, those systems, if you remember using them 5 or 10 years ago, have been utterly transformed by deep learning. And then I want to talk about sort of general purpose AI. And that then is this question of, well, it's not specialized, right? It's how do you, I mean, humans are just so flexible and adaptable. They're able to transfer their learning from one environment into another environment to do, you know, creativity, long-term planning. And this is what's called general purpose AI. And so some, you know, I've heard people say, oh, the AI problems are basically solved, right? Not true. But if they're saying that, it means that, well, it's probably over here. I think here, we just have so far to go in understanding what intent is, what does it mean to do AI in context? Can an AI system understand the context? Can it understand emotion? Can it understand goals? And make that part of this human technology frontier. Okay, so I want to just talk about a few challenges here and here. So let me, how many people have seen this stop sign example before? Okay, so this is a really, so it was in CVPR conference, I think last year. So this comes out of a paper from Berkeley, Michigan, Wisconsin, no, Washington, and one other school. And so it's an adversarial AI problem, okay? So what happened was, so you've got a classifier that's trained to recognize stop signs, okay? So you're given the classifier, and you're given the stop signs that it's been trained on. Here's your task. You're given a bunch of pieces of paper, black and white rectangles, and you're allowed to put them on stop signs. And the question is, can you put them on a stop sign so that the stop sign is not recognized as a stop sign? In fact, it will be recognized as a 45-mile-an-hour sign, right? So the opposite of stop, right? And so in this adversarial paper, they were able to show that in 100% of the cases, they were able to arrange these I mean, you look at that, right? What is that? That's a stop sign that somebody's put some pieces of paper on, right? You know that as a human. The algorithm, the network that was trained to recognize stop signs doesn't have that common sense reasoning, right? And if you know what the training data set was and what the algorithm is, you're able to figure out how to put up these pieces of square, you know, black and white paper in order to fool the algorithm 100% of the time. And so to me, that talks about the real fragility of where we still are with classification algorithms, right? We don't understand really why it is, what is it about a stop sign? What's the essence of a stop sign that we're trained to do classification, but sort of that deeper level real world understanding is missing here. So I think that is a huge challenge, especially if you're thinking about deploying algorithms, classification systems in practice, where really it's a life-saving or a life or death issue that you do classification correctly. So I'll come back to that. You all know about the importance of data. I'm sure you're all concerned about privacy issues with data. There's just some, I don't know if you haven't read this CryptoNets paper, it's really another one of these eye-opening papers that I read not too long ago. This comes out of Microsoft research, primarily in Columbia University, that when you're doing your when you're doing your classification, what you're doing is you're doing classification not on an original image, but on what's called a homomorphic encryption of the image. So what you're doing is you're doing classification, but you're doing classification over encrypted images. The answer that comes back is encrypted, but the original picture in this original image that you're trying to classify, you get back the right answer for that original picture, right? And so what that means, if you're a cloud provider, for example, it means now you're doing classification, this issue of, well, I'm sharing my data. Maybe you want people to share their data with your company, but maybe not everybody wants to make their data public, right? And so now we can potentially do classification, obviously not at the speeds that you could do normal classification in real time, but you can do classification on encrypted data and return encrypted classifications. And to me, I think that's a profound step forward. Okay? So, I'm a professor, so I get to assign homework, but you don't have to do it, right? But this paper and this paper are great reads just to see some really neat work. Okay, so I would call these both instances of challenges in narrow AI. And I want to show you a video. So this comes from a researcher named Josh Tenenbaum, who's actually a social psychologist at MIT. And what this video sort of gets at is a grand challenge in AI, and it's really, you want to watch this little kid over here, right? Because it will show sort of how flexible, how adaptive, and how context sensitive even a 2-year-old is. And that kind of intelligent, flexible, cooperative behavior, imagine that's a robot, not a 2-year-old kid. This kid's going to do exactly what you'd want a robot to do, but we're still so far away from being able to do this kind of intelligent, flexible, and general cooperative behavior. So let me see if I can make this work.
The subject in the experiment is the little kid who's watching, and he doesn't know what's going on any more than you do. But think about what's going on inside his head. He sees Felix banging against the cabinet. It looks like he needs help. How do you know that? Well, watch what the kid does. You got it.
So having 2 grandkids who are about that age, I love that video, right? It just absolutely so perfectly sort of shows you what we really want to strive for in the AI systems that we're building, that understand context, that understand intent, that do more than classification, right? But and that's a long-term, as the MIT professor there said, that's a long-term grand challenge in AI and something that is still out there. Okay, I'm going to go through these pretty quickly. It's because I want to get to the educational part, but especially within the Department of Defense in the United States and also within the National Science Foundation, this notion of explainable AI is something that has become very important, or realized as being very important. So many of you know about sort of the basic way that we're doing classification through classifiers, that they can be very, very accurate, do amazing things. But if you ask, why did that answer come out? Why did you make this prediction and not that prediction? Why, if there was a mistake, can you query the system in order to understand what the mistake is? That's still not out there. So the goal is to be able to take images, put the new images through a classifier, do prediction, and then be able to query that classification algorithm to tell you why. So imagine you're a radiologist. So this is the sort of the best example of all. You're looking at chest x-rays, you make a diagnosis, the classifier makes a diagnosis, and now the doctor, physician wants to interact with the AI system to understand why was it that that classification was made and not another, why was one diagnosis made and not another one? And so this is going to be very important. I think also when we as, computer science savvy people want to have our systems used by people other than other computer science savvy people, these are the kinds of questions that we're really going to have to address here. Okay, so this leads into this notion of something called what's being called trustworthy AI. And there's not a definition for this, but here's a start, right? It needs to be able to function reliably, needs to be able to explain its conclusions, not violate privacy, and not exhibit biases. So I'm sure you've all read a lot about bias in the bias the input data. Of course you're going to bias the decision making. And so there's a lot of activity going on in the United States around this notion of trustworthy AI. So we at the National Science Foundation teamed up with Amazon for an $11 million program on fairness in AI systems. That's actually throughout the entire AI system lifecycle. We teamed up with the Partnership on AI to look at AI and society with some ethics there. And then we have a solicitation out to build what we're calling research institutes. And one of those research, or a set of those research institutes, will be around these issues of fairness, accountability, and transparency, or other words, trustworthiness. So I think this is a really important area. If you want your customers to trust your systems, and we want people to use the systems that are being engineered, this issue of trustworthiness is going to be really central. So there's an organization, have people heard of the OECD? Maybe read about it in the newspapers, right? It's a set of 35 liberal democracies, Korea, Japan, the United States, many of the European countries are part of this. There was a group that met for about a year and a half, so I was part of that group. It was led by, actually, the person who chaired this group was a Korean named Wang Ki-min, who's your ICT vice minister, I think, anyway, an amazing guy. This group came up with these 10 sort of OECD principles on AI. And so you see these notions, I think things I would stress are things about human-centered values, right? And fairness, and of course, transparency, we saw explainability, accountability. These all sort of make trustworthy AI, all of these together. And for me, as someone very interested in research, and think that's incredibly important, one of the major recommendations is for all of our countries, so your country, my country, is to continue and really double down on the investment in AI R&D. Okay, so let me stop there. Any comments or questions? Sometimes when I teach, to force people to ask questions, I get down on my knees and beg for a question. I'm not going to do that here. Anybody want to make a comment or a question? It's okay. All right. So I'm going to just go through very, very quickly. The take-home message here. I want to talk about AI systems, and I think one has to define what that term means. And what I want to talk about is how I know there's a lot of work going on here, right here in this particular area, but that all the way up and down the stack, lots of different parts of computer science are going to need to be involved here. Okay, so let's start down here. Obviously, for machine learning in particular, it's got to be supported by large amounts of data. And so you see IoT, the scientific instruments. So actually, for doing the new telescopes that are being developed now that'll be functional in another year or two are going to be able to do complete scans of the entire night sky twice per evening. And then all that data has to be processed, and you have to look for interesting phenomena in that. And that's only going to happen with sort of machine analysis, computing analysis of the data coming in from these telescopes. And that's going to require machine learning algorithms to do that kind of change detection. So there's sensing, there's data acquisition, there's the detection. We're going to need data at a very large scale. That data is not going to all be in one place, so it's going to be distributed. What's the networking? What's the system support for that? And then issues of how do I find my data? Because I forgot to ask whether you're doing things on data search here. Google's started up a really interesting project on data set search. How do you locate data sets as opposed to locate web pages and resources and documents, but data specifically. So data discovery, I think, will be a very important challenge, locating publicly available data sets, and then the issues of security and privacy around them. Okay, so machine learning, we talked about the stop signs example already, so safety, predictability, the fairness, accountability, and trustworthiness, and then all of the machine learning, types of different machine learning algorithms that you folks are working with here. At a higher level, we're going up the stack, we're getting to almost the cognitive level now, right? So this is effective computing, sort of understanding human emotional state. I talked about classifying interesting astronomical events. And then here, we were having a conversation earlier about knowledge networks and how knowledge networks, this notion that, well, I've got this person named Steve, who's the CEO of Microsoft, which is an organization. And so we're relating concepts. And now when we're doing search, instead of searching with keywords and keyword proximity and things like that, we can do a much more semantically rich search. So for example, if I ask you, is there abnormal rainfall in San Diego? And that's a question I type into your search engine. If you understand conceptually what San Diego is and rain, you may turn up a data set that talks about Southern California by zip code, but not calling it San Diego, and precipitation using the word hydrometeor or something, a different term, but understand that those are semantically equivalent and return those kinds of answers. And so this kind of knowledge representation, I think, will be very important in the future. At the National Science Foundation, we started an activity, together with universities and also some of the large search companies in the United States about the possibility of an open knowledge network so that people could do proprietary parts, but there would be open parts to it as well. This would be computing infrastructure that could be used that would help in better search, for example. We need the AI infrastructure, we need the networking, the computers, the instruments, and the storage. There's a picture of an open knowledge network. It's really a part of AI infrastructure. And then, of course, we need the people and the organizations to support all that. Okay, so I'm going to finish up my discussion of AI here just by saying that it is definitely a national priority for the United States. So our current presidents, I want to say, I've served under 2 administrations now in the United States. Both were very interested in artificial intelligence and promoted it and the funding of it, of research, quite a bit. Our current president issued an executive order sort of declaring this to be a national priority for funding. There's a I'll give this to you as homework also, if you want more. Students never ask for more homework. This is the National AI R&D Strategic Plan. It was updated just 4 or 5 months ago. And so a copy of these slides, if you need the homework assignment, I'm leaving behind a copy of these slides. So this actually makes for pretty interesting reading. It updates a plan that was done, that we worked on 3 years earlier. It updated it this past summer, talking about what are the areas in which the government-funded agencies and also the US academics funded by government agencies, what are priority areas there? And then we saw the OECD AI principles there, where they talk about trustworthy AI being particularly important.
So one question about the strategic plan.
Yep.
So that is for the US.
That's for the US.
For the US and China are kind of leading the AI field right now, right? So do you think that this strategic plan is also relevant for smaller countries like Korea, or I'm from Sweden myself?
Yeah, I think, so if you look into this, you'll see that there are, I think, 9 different areas in there. And it's really, it's not really geared towards a particular country. It doesn't say, for instance, that, oh, because we are the United States, we have this interest. It says instead that there's a section on trustworthy AI, for example. And no matter where you are, no matter where you live, what country you're in, that's absolutely important. There's an issue there about data and privacy, and there's a section in there about fairness and bias. And so I think what's in here absolutely transcends any particular country. All right, I'm going to finish up here just with a few thoughts on universities, because I'm a university professor. You all look like you're relatively recent out of university, so hopefully you still care. You're new. The people who work here are coming out of university, so you should care. Okay, well, you saw this slide already about where jobs are, the numbers of majors and things like that. What I want to do is I want to tell you 3 things. Some things happening with high school students, right? Because that's the beginning, or middle school. That's the beginning of the pipeline. What's happening at the undergraduate level, and what's happening then at the graduate level, and then we'll be done. Okay, there's a program in our initiative in the United States called Computer Science for All, and here's the goal: rigorous and effective computer science education available to all high school, and middle school students. Okay, so in the United States, it's been very, in the town I live in, we have 1 computer science teacher, and she doubles as a math teacher, and there's not a lot of courses available for high school students. So this was amazing. So it's always great when you're working somewhere. So I was working at the NSF at the time, and the president, who does a weekly video address, I'm not sure our current president does, but our previous president did, came out and talked about computer science. Nothing better than having your president say what you're doing is important. And so, he was really talking a lot about computer science education here. Okay, so that's the goal here. And the question, and I know things are different, maybe a little bit more top-down in Korea in education. In the United States, it's very bottom-up. Every town sets its own it decides what's going to be in its local curriculum. So in Massachusetts, the state I live in, there's 406 different decision makers about what gets taught in high school. And the question is, and Massachusetts is a pretty small state, right? And so the question is, how do you get a high quality computer science education into a school system, a national school system that's very decentralized? And the way that was done was through what's called an AP, Advanced Placement Exam, on computer science principles, okay? And so what this did was, this is an exam that high school students can take. If they get a good grade on it, then you get credit in college, and so it's less college work that you have to do. And so this was designed to be rigorous. It's a new exam. It started in 2017. The new exam. It's rigorous. It's not just coding. Matter of fact, it's only about 1/7 coding. Question? Yes.
They already have an APCS.
Yes, exactly. So this is a second. That's a great point. This is the second. It's a new AP exam. So there's an old AP exam which still exists, which is it's really about problem solving and programming, right? This one is much more about the application and creative use of computing. So there's 7 different modules, one of which is programming, but there's also data, there's also things about the internet, how to creatively apply computing, how to think algorithmically, computational thinking. So this is a little bit broader, and it pulls in, actually, the interesting thing is it pulls in a much more diverse set of students who actually take this course rather than the programming-based course, right? So we've got now 2 CS AP exams, and let me show you the data for these. So what's being plotted here, so the exam was introduced in 2017. This is looking at the number of women who take an AP exam in computer science. This is the number of Black and African American students, and this is the number of Hispanic students. And so, I don't know what the diversity statistics here. It looks about right if you're a representative sample, the same as in the United States. There's an issue that the people the students going into computer science aren't in the same proportion representative of the population. So this is something really important. When we say computer science for all, I always like to say computer science for all, meaning for all students. And so you see how the pipeline here has really been broadened. And you see the participation of women and underrepresented minorities in the space of 10 years going from 18% to 29% and 12% to 22%. And so that's actually something that's really, really encouraging, that the students coming into the pipeline are much more diverse than the students that have been traditionally coming into our pipeline. Okay, so that's high school. At the undergraduate level, we were talking, we sort of went over this once before, about the growth of the field of computer science. So yes, we have more computer science majors. Honestly, where the real growth is going to happen is in something that we sometimes call CS plus X or X plus CS. Because I try not to say, I wrote it up there, I'm gonna switch it right after this. We call it X plus CS because you never want to put yourself first, right? It's like, well, we're at the center of things and then there's everybody else X, right? Really, X is way bigger than computer science, right? And so, we are being called on to produce. It's just going to be more important for many more people to have an understanding of computing and how it works. It will help them in their jobs in all kinds of other disciplines, whether it's in other science disciplines. So you're an astronomer, right? You're looking for evidence of neutron star collisions forming black holes in pictures streaming off of images streaming off a telescope, right? Well, okay, you better know something about algorithms, right? And of course, you better know a lot about astronomy to do that. If you're in health or medicine, if you're in the digital humanities or art and design or social science. And so the idea is that we will be having students who have a grounding, not as broad and as deep as if you're computer science majors, but not shallow either, with a firm grounding in computational thinking and algorithms and systems, and also data science, and then they'll apply those in different fields. And so this is happening actually on a lot of campuses right now. It's happening on my campus. When we talked about why we should be a school of computer science and not a department of computer science, it was really because of this, right? We are reaching out from computer science to all these other disciplines and saying, oh, you know, we can do these new interdisciplinary majors together. Okay, let's pop up to the graduate and actually the professorial level also. So I don't know, these are some of the, you know, I read the New York Times every day. It's where I get my news. I have friends who were computer science faculty and are no longer computer science faculty. If it's not obvious, I love being a professor and being a computer science faculty member. But I understand that there's a lot of draw to working at a company like Naver or, you know, lots of other companies, right? And so, you know, there are faculty who are making this transition from being in academia to working in industry. We also see, and this is maybe even more worrisome, students who come to get a PhD, get to their master's level, and then decide, oh, I'm going to industry, and don't get a PhD. I could talk about why that's a worry, but we'll leave that for another time. The interesting thing to me is when I talk to my friends about, well, why is it that you went to industry from academia? So the interesting thing is they don't say, I did it for the money. No one has ever told me, oh, I went to work for, I shouldn't name a company, but you know, pick your company, right? I went there because I'll make a lot of money, right? Professors in the United States are actually paid pretty well, right? I mean, not as much as in companies, but people, the reason that they're giving is, well, I'm not going to work for, I'm going to try not to mention any company. Some company, right? Some big company that neighbor, right? Okay, I'll pick on you, right? You know, why do you go there? Well, what they say, not for the money. They go there because of the impact, right? That, oh, you know, I will see my code out there being used by millions of people, right? I mean, we all want to see something like that, right? We were talking earlier about A/B testing, right? If you're a faculty member and you've got a better idea how to do X, right? And now you want to try it out on people, you know, your academics are not in a position like you folks are to actually integrate it into the system. You know who your users are. You can select statistically identical populations at scale. Try it on this, try something else on this, look at the difference and do that kind of A/B testing. I mean, you just can't do that in academia. I want to make the case that that's a great reason to try to make partnerships between academia and industry so that that can be done together. There's also resources. So engineering staff, you know, people who are going to build things for you, the data that you need access to, and the computing resources that you need access to. And so notice I don't have salary or money up there. So I sort of get it. I totally get that. So you can see that this is something that is in the forefront. When it starts showing up in the New York Times and the Washington Post, you know that people are broadly thinking about it. Just with respect to this issue of resources, I want to show you a graphic that I found that I find really interesting. So this comes from OpenAI. So here's the year. Now normally, you know, you're used to seeing Moore's Law here, right? So this is the opposite of Moore's Law. This is looking at how many, so here's time. We're plotting different AI systems you'll recognize. So there's AlphaGo 0 and AlphaZero way up there at the top. And what's being plotted here are the number of petaflop seconds per day that are needed to train. So it's an amount of computation that was needed in order to train the system, right? And a petaflop second day is about 10 to the 20th operations within a neural network, okay, in a day, right? And so what you see is this, so first of all, notice this is a logarithmic scale, right? And so you see that, you know, as the systems sort of go on, here's some speech analysis, you see that basically it's doubling every, I think it's 83 days, the amount, you know, if you look at what the slope of this line is, right? And again, that's not the kind of computation. I don't know what kind of computational resources you have here, but I do know, or I'm guessing, that they're much better than you're going to find, or much richer and much more massive than you'll find in a typical university, right? So another reason that if you need computation at scale, getting that is something that's getting harder and harder to do in academia. Okay, finally, and I think this is my last slide, about rethinking computer science departments in universities. So I mentioned already this trend in the United States towards colleges of computing. And so, Carnegie Mellon has had that for 30 years, Georgia Tech for 25 years, my university, UMass, 3 years now. MIT announced a school of computing this past February. And so, to me, again, this sort of reflects that picture of computing being at the center of the universe. And the one other thing I wanted to note here is sort of what's happening demographically. So in the United States, the number of kids who are 18 to 22 is actually shrinking, right? So the college-age population, the number of students who can go to university, could even possibly go to universities, is going down. And actually, this is true in Korea too. So here's a graphic a friend of mine showed me. And so this is looking at the demographics of male and female by age. So that's on this axis in Korea, 1960. So you see that curve just sort of going up. So, most of the distribution is at the young age. This is in 2010, right? So look at how that distribution has skewed itself already here, right? And the same thing's happening in the United States and in another number of other countries, as you've probably read, particularly OECD countries. But I thought this is the most striking graphic I've seen to sort of show that. So the question is, what does that mean if we have a decreasing 18 to 22-year-old population? So you're in a university. What does that mean for you? Well, here are the factors, right? We've got a smaller population. Actually, I don't know how education is financed here in Korea. In the United States, there are public schools and there are private schools, but both of those are pretty expensive, right? The private universities in the United States are about $70,000 a year. That's a lot of money, right? Have 3 kids. I had 2 kids in college at the same time for 6 years, right? So, do the math, right? It's a lot of money, right? That can't continue, right? Those costs cannot continue to go up. Now, think about yourselves and think about how jobs are being disrupted by technology. And hopefully, I'm sure you've all realized that whatever you learned while you were 18 to 22 and being in college is not going to be sufficient for your career, right? And so we've got this issue that much more lifelong learning is going to be required. And, so this notion of what it means to be in a college, this notion that maybe I want to do some work while I'm in college, so I'm not going to be in college, I'm not going to be on campus, so I need to get my courses somehow. I might do asynchronous learning and be off campus, and I need to do that throughout my lifetime, right? And so this is longer term reading, so it's not due on Monday. I'll be back on Monday to collect all the homework. But this is a really, I don't know if you've read Clayton Christensen. He wrote a book called The Innovator's Dilemma that actually, since you're in this company, if you haven't read it, you should, right? Because it talks about how companies that are formed and are incredibly innovative and they move to the top of their field and they capture market share, how hard it is for them to continue to innovate, right? And I won't name any US companies that I could point to that have had that problem, but the book talks about that. This book talks about disruption in the innovative university. Okay, that's for your interest reading. For extra credit. Good. Okay, so innovate or die. That's sort of a famous saying from Peter Drucker in Forbes magazine. So the question is, how are universities going to step up to this challenge? And really, all the universities globally are going to be facing this challenge. Simply by saying, have you seen the movie Forrest Gump? Yeah? You know how in Forrest Gump he just sort of always shows up at the most amazing points in time. And I feel like, I went into computer science because I love to code, right? I found that out on a really old IBM machine that is now in museums. But I love to code, right? And so that's how I went into computer science, because I love computer science. And in that time, it's become the case that computing is really everywhere. It's important, beyond science and engineering to all of society. It intertwines with all these different communities that we've talked about, and there's so much going on, right? It's going to be changing universities. It's changing its structure within universities. It's just, you see this when it must feel great to sit on a subway and see people using your company's products all the time. So when I was riding the metro the other day, my first time I've been in Korea, I just saw everybody using your apps. And so it must be great, right? So much is happening, and yet, if you want to continue to innovate, if you want to be thinking about the future, things are changing so quickly that there's tremendous opportunity. And so I think, again, that requires everybody, all hands on deck, as we say. Okay, so that's it. I want to say thank you for inviting me, and thank you for the comments and questions, and be happy to hang around and talk with people also. So thank you.